Okay, section 6.3 deals with the Graham-Schmidt process, QR decomposition, orthogonal and orthonormal sets. We already talked about orthogonal and orthonormal sets, but just recapping those definitions, we say that a set of two or more vectors in a real inner product space is said to be orthogonal if all pairs of distinct vectors in the set are orthogonal. Right, that means that for any two vectors you choose in the set, they will be orthogonal to one another. And when are two vectors orthogonal? You need to check their inner product. So we say two vectors u and v are orthogonal if their inner product is equal to 0. Okay. Now, an orthogonal set of vectors where each vector has a norm 1 is called an orthonormal set of vectors. So in that orthogonal set, if every vector has norm 1, then we say that it's orthonormal. So given the following example, if we look at P2 defined with the inner product, where the inner product is given by the integral from -1 to 1 of the product of the two functions, then they just ask us to show here that this set is orthogonal, and then they want us to normalize each vector, and we normalize each vector by multiplying it with 1 over its norm. Right, so let's take vectors P, Q, and R respectively, and what we're going to do now is we're going to take the inner product of P with Q. So we're going to take the inner product of P with R, and then we're going to take the inner product of Q with R and show that they are all equal to 0. Right, so if we take remember to show it's an orthogonal set, we need to check that for every pair of vectors within the given set, we have orthogonality between those two vectors. And you must be able to do it for all pairs. So looking at the inner product of P with Q, that's defined as the integral from -1 to 1 of the functions P times Q, which is x cubed. And then working that out, we get that result there. Okay, so it's clearly 0. So the next one we want to do is we want to look at the inner product of P with R. Right, and that is the integral from -1 to 1 of the function P, which is x, multiplied by the function R, which is 1 minus 5 over 3x squared. And that is simply the given function, and then working that out, we get that result. Okay. Right, so the next one we want to look at is, so we've paired off P and Q and P and R, and now the last one we need to check is we need to pair off Q and R and just check that that's 0 as well. Right, so the inner product of Q with R is defined as, it's the integral from -1 to 1 of the function Q with multiplied by the function R, which in this case is x squared multiplied by 1 minus 5 over 3x squared, and that then becomes the integral from -1 to 1 of this function here, and then going and working that out, we get, alright, so we can say then it follows that this set here is orthogonal. Right, so now are asked, remember we are asked to find a orthonormal set of vectors, right? So we need to normalize this set of vectors. Now to normalize the set of vectors, we need to know what their norms are. Okay, so we're going to note that. So we're going to work that out. Right, so that's the integral from -1 to 1 of the function p multiplied with the function p. Remember, p was the function x, so that's going to be x squared. And then working that out, we get that is in fact 2/3. Okay, so the norm of p. Remember, the norm of p is going to be the square root of the inner product of p with itself, and that is going to be the square root of 2/3. Okay. Right, next we've got the inner product of q with itself. Right, so that is the integral from -1 to 1 of the function x squared multiplied by the function x squared, which is x to the 4, and then working that out, we get then that that becomes 2/5. So the norm of q is going to be the square root of 2/5. Right, the last one is we need to work out the inner product of the function r with itself. Right, so the inner product of r with itself is going to be the integral from -1 to +1 of the function r multiplied by the function r. So the function r in this case, recall, is 1 minus 5/3 x squared. So you're going to multiply 1 minus 5/3 x squared with itself, and you're going to get the integral from -1 to 1 of the function 1 minus 10/3 x squared plus 25/9 x to the 4. And that is equal to 2 times the integral from of this function here from 0 to 1, because this function here is symmetrical about the y-axis. So therefore we can just go from 1 to 0 and multiply it by 2. Okay. So that is then equal to, right, that's equal to 2 times 1 minus 10/9 plus 5/9. And then that is equal to 2 times 4/9. And this implies then that the norm of r is going to be the square root of 8/9. Okay, so normalizing the vectors, we get the final set. So remember this set we calculated that it is in fact orthogonal, and remember the norm of r to be 8/9, calculated the norm of q to be 2/5 square root, calculated the norm of p to be the square root of 2/3. So basically orthonormal So the orthonormal set is basically the set that we form by taking the vector x, Okay, and what we do is we divide it by its norm. And so this vector, x over the square root of 2 over 3, if you go and work its norm out, it's going to be 1. So then you take your second function and you normalize your vector x squared by dividing by its norm. Okay, and right, you divide it by its norm. That's going to be a vector of norm 1, and then you take your last function or your vector and you're going to divide it by its norm again. And we calculated the norm of this function as the function or the real number square root of 8 over 9, and that is your orthonormal set. Okay, so this example just basically looks at as illustration of the definition of the difference between an orthogonal set and an orthonormal set. All right, because we're going to need this definition for the other results in this section. Right, next up we've got Theorem 1, which just says that if you've got a set of vectors that happens to be orthogonal, and these vectors are all non-zero in an inner product space, then we can say that S must be a linearly independent set. So if they're orthogonal, automatically they're going to be linearly independent. And again, we need this result for the most important results in this section. So let's just quickly look at why this is in fact the case. Right, so we claim that given a set of vectors that are orthogonal, we need to show that the set S is linearly independent. Okay, right. So let's suppose to the contrary that S is not linearly independent. Right, so suppose that S is not linearly independent. So what does that mean? It means that we can express one vector as a linear combination of all the other vectors. Right, so that means without loss of generality, we can find real numbers ki. Right, we can find real numbers such that for ki we have where I runs from 2 up until r, we can then express the vector v1 as a linear combination of all the remaining vectors in the set, like that. And just remember that we can assume without loss of generality that this is a non-zero constant. And again, remember S is a set of non-zero vectors. Remember, as S is orthogonal, we have that we can take the inner product of v1 with v2, and basically we can replace the vector v1 by that sum, a linear combination of vectors, because remember we expressed v1 as that whole vector there. Right, and using our rule, our axioms of inner products, that then we can replace that with this sum here. Remember, it's the axioms that I've used. Recall that we know that if you've got the inner product of u with v, well, if you've got the inner product of a scalar multiple of the vector v, u with v, remember you can replace that with that. And also if you have a sum between two vectors and you take the inner product of u plus v with w, it's simply u with w plus v with w. Okay, so this rule we just repeatedly apply, and this one as well. and then we get that sum, right? Now remember that S is an orthogonal set, so it means that for any pair of distinct vectors, we get that their inner product is 0 because they're orthogonal. So what's going to happen here is this is going to be 0. All these terms are going to be 0, with the exception of possibly this one here. Right, so that's going to, everything is going to fall away there, and you're going to be left with K2 V2 with itself. And that, we know, is basically the norm of V2. Now, in addition to that, that inner product V1 with V2 is also going to be 0 because V1 and V2 are orthogonal. So from there, this is then going to imply that it's going to imply that this thing that we have here, that is going to be, it's going to be equal to 0. Okay, so it's going to be equal to 0 there. Okay, and because K2 is a non-zero real number, we're going to have that, basically it's going to imply that the norm of V2 is going to be 0, or norm of V2 squared is going to be 0, which is going to imply that the norm of V2 must be 0. And the norm of a vector, if it's 0, it means that the vector itself is 0, a 0 vector. Okay, but we said S is a set of non-zero vectors. So that is a contradiction. Okay, right, so that can definitely not happen. So a contradiction, right, so that is just not possible. Okay, so therefore any set of orthogonal vectors is always going to be linearly independent. Alright, so we have verified that. So in an inner product space, a basis consisting of orthonormal vectors is called an orthonormal basis, and a basis consisting of orthogonal vectors is called an orthogonal basis. Now if you go back to the previous example, we said that in P2 is the set of all functions of degree, or polynomials rather, of degree at most 2. If we look at the previous example, that is a set of orthogonal vectors. We verified that. And by Theorem 6.3.1, any set of orthogonal vectors is going to be linearly independent. So this set of vectors x squared 1 minus 5 over 3x squared, that is going to be a linearly independent set, and therefore it must be a basis for P2, because remember we said in a finite dimensional vector space, if the dimension of P2 is equal to 3, right? So if you take any set of 3 vectors, if that set is linearly independent, then automatically it's going to be a basis. And remember that result, if it spans, if that set of 3 vectors spans the whole vector space, you don't have to check the linearly independence, it's going to be automatic. And if you have the linearly independence, then the span property is going to be automatic, and that happens when we've got a finite dimensional vector space. So this is going to be a basis, and on top of that it's going to be orthogonal basis of P2 with the inner product, that particular inner product. Okay, so that's a useful little result there. Right, next up we've got coordinates relative to the orthonormal basis, right? So in Theorem 6.3.2, if S is a orthogonal basis for an inner product space V, and U is just any vector in V, then we can express U as that linear combination there, where we can actually determine those coefficients as the given values there, defined in terms of the norm and the inner product. Then also, if S is an orthonormal basis for an inner product space V, then obviously the norm of each one of those vectors V1 up until Vn is going to be 1. And so again, we can go and replace each one of these norms with 1, and so that then reduces to this here. Right. Okay, so let's just quickly look at why we can express the vector u in that form. Now remember, in chapter 3 we did that projection theorem, so some of that stuff is going to become relevant again now. So let's just quickly look at why we can express the vector u in that way. Right, so let's look at the proof. Remember, S is a basis. Right, so again, S is a basis, yes, and S is orthogonal as well. Don't forget that it's orthogonal. So because S is a basis, we have that there exists real numbers k1 up until kn, such that we can express u as a linear combination between the vectors in the basis. Alright, so that is known. But also, the set of vectors in S, they are all orthogonal. Now this means that firstly, we are going to take the orthogonal, we're going to take the inner product of u with the ith vector, right? Now remember again what I said is all these v's are orthogonal to one another. So then we can replace the vector u with its linear combination, which is this there. Alright, and then again using all my axioms, the ones we just discussed, we get that we can then replace this whole part with this sum here on the right hand side. Okay, there's my kth inner product, and there I go up until the end. And that is just both those axioms that I'm repeatedly using. Now what's going to happen, V1 and Vi, they are orthogonal, so that's going to fall away. That is going to fall away. Everything is going to fall away except for possibly this term here. Right, so we can go further and then say that we can then go and replace that with the term ki vi with itself, and that is basically ki with the square root of the norm of v, not the square root, the square of the norm of vi. Right, now that means that again we can go and solve for this value here, and that's going to imply that we can solve for ki as what? We can solve the for ki as that divided by the norm of vi squared. Right, okay, and we can do this for all i's, so for every I. Right, so this is that's done for all I, and I is an index, goes from 1 up until n. Okay, so that proves the result. Okay, so we can then go and replace each one of these k's with its respect. So we can go and replace k1 with what we get for k1 there, and k2 for what we get for k2 there, and so on and so forth, and get my result. Right. Now, just one point of interest. Again, the coordinate vector of a vector u and v, remember, S is the basis. Where S is orthogonal, the coordinate vector with respect to the basis S is pretty much formed by all the coefficients. Remember, if we go back to this result here, you can see the vector u and all its coefficients that you solved. And basically that is the coordinate vector relative to the orthogonal basis. And also the coordinate vector relative to the orthonormal basis will be this vector here, the orthonormal basis being v1 up until vn, and because it's orthonormal, each one of these norms is equal to 1. So basically it's going to just become that. This brings us to the example. Let's look at R3 and the Euclidean inner product. That we know is a we know what the Euclidean inner product is. It's the normal dot product, and we're basically asked to show that the vectors v1, v2, and v3 that set is an orthogonal basis for R3, and then in the second one we are just asked to find the coordinate vector of u relative to the orthogonal basis S, and u is given as 1, 2, 3. So it's just an application of this theorem that we just proved now. And the first thing would be to show that it's a basis, and that's easy to do. Right, so there we've got our three vectors, and we are asked to show that this set of vectors is firstly we need to show that it's orthogonal. So taking the first vector, and then what we do is we take the dot product with the second vector. This is the Euclidean inner product. And the Euclidean inner product is the traditional dot product that we're working with. So we're going to take the dot product of those two vectors, and that is the dot product between this vector and that vector. Okay, and that is just going to become 0. Then we're going to take the vector v1, and we're going to take the dot product with the vector v3, and that becomes the dot product of the vector v1 dot vector v3 okay, and that is again going to be 0. And then lastly we take the dot product of the vector v2 because we're taking them pairwise, and we're going to take the dot product with the vector v3. And that is the dot product of this vector here with the dot product of that vector. Okay, and then taking the dot product there, we again see that that is 0. Okay, so the conclusion we can make from this is we can say that S is orthogonal Now previously we did a theorem which said that if you've got a set of vectors that's orthogonal, in other words each pair of vectors within the set are orthogonal to one another, then the set must also be linearly independent. Right, so S is linearly independent. And we have from chapter 4 that if you've got a finite dimensional vector space and then it's only enough to check whether a set is a basis. You only have to make sure that it is, firstly, it's got the same number of vectors as your dimension, and it must be linearly independent, or it must span the whole vector space. It's enough to check only one. We don't have to check span and linear independence. We only have to check one of the two. And because S is linearly independent, it follows that S is a basis. It's a basis also, right? And therefore it is a orthogonal. It's an orthogonal basis. Right, now we're asked to find the coordinate vector relative to this basis S, where U is the vector 1, 2, 3. Right, so there we're given the vector U and the basis, and we know that the orthogonal, or the coordinate vector relative to the basis S is this vector here. It is going to be the inner product of U with the vector 0, 1, 0 divided by the norm of the vector 0, 1, 0 squared. Then it's going to be the vector U's inner product with the second vector in the list, which is 1, 0, 1. Okay, and we're going to divide by the norm of the vector 1, 0, 1 squared. Alright, and the last one is going to be, it's going to be the inner product of the vector U with the vector 1, 0, minus 1. Okay, and we're going to divide that by the norm of the vector 1, 0, minus 1 squared. Right. Okay, and we know what the inner product in this case is. It is the Euclidean inner product. So that is going to give me the vector 2, or the real number 2. And the norm of 0, 1, 0 squared is 1. Second one is going to be the dot product of U with this vector here, which is going to be the vector 4. Not the vector 4, the real number 4. And you're going to divide that by the norm, which is going to be 2. And then the last one is going to be the dot product between U and the vector 1, 0, minus 1, and that's going to be minus 2. Right, and so that's going to be the vector 2, 2, and minus 1. Right, next up we've got the projection theorem. We've already done a special case of the projection theorem in chapter 3. Just to recap on how it works, if we look at theorem 3, now what we're going to do is we're going to project orthogonally a vector U onto a finite dimensional subspace W. Of an inner product vector space V. Then every vector U in V can be expressed in exactly one way as W1 plus W2, where W1 is in the subspace W and W2 is in the subspace W with that little sign there. And remember what that was? That is the orthogonal complement of W. So it's all vectors that are orthogonal to every single vector in W. Now, just an illustration. If we had to look at what we're dealing with here, W is the subspace, and we want to orthogonally project U onto W. So we can select a vector in W, call it Z1, and we can select a vector Z2 that is in the orthogonal complement of W. Then basically what you have is you want to go and orthogonally project this vector U. You want to go and orthogonally project it onto the vector Z1, which is what we're going to do. So that's the vector W1. That's the orthogonal projection of U onto W. Okay. And then what you want to do is you also want to take the vector U, and then you want to orthogonally project it onto the vector Z2, which gives you that vector there. Alright, so that is essentially what it is that we want to do. Okay, so again, if W is a finite dimensional subspace of an inner product space V, then the unique vectors W1 and W2, such that U is W1 plus W2, these are called the orthogonal projections of U on W and the orthogonal projection of U on the orthogonal complement of W, respectively. And they are basically denoted by W1 and W2 respectively. Now, alternatively, W2 is called the component of U orthogonal to W. And moreover, the projection of U onto the orthogonal complement of W is simply U minus the projection of U onto W. Right, so remember what you're doing now is you're taking the vector, and what you're doing is if you orthogonally project it onto this vector Z2, that is W2, and this one here that you do there, that is the vector W1, the one that you orthogonally project onto the subspace W. So that's the projection of U onto W, and that's called the projection of U onto the orthogonal complement of W. Okay, so we can express U as the projection of U onto W plus the projection of U onto the orthogonal complement of W. Alright, so as indicated there with the red vectors, both add up to the vector U. Right, and we can just replace the projection of U onto the orthogonal complement of W with the vector U minus the projection of U onto W. Right, one last theorem before our main result. If you look at Theorem 6.3.4, let W be a finite dimensional subspace of an inner product space V, and if that set is an orthogonal basis for W, and U is just any vector in V, then we can go and project U onto W, and that is going to be this linear combination. And if it happens that the set of vectors is an orthonormal basis, meaning that the norm of each vector in this basis is 1, then this projection reduces to that. And it's simply so because all we do is replace each one of these norms with 1. Right, so let's quickly go and see why this is the case, why we can represent our projection of U onto W in that way. Right, now recall that W1 was the vector that's the projection of U onto the subspace W. And what was W1? Again, it's that vector in W. Now, W1 can be expressed as a linear combination of the basis vectors. In the previous theorem, if you have a set of orthogonal basis vectors, then you can express you can express this vector as a linear combination of these basis vectors, and the linear combination looks like that. And we calculated each one of these coefficients to get our linear combination. So we can express W1 as that linear combination of, as I said, these basis vectors. And remember, the V's are the basis vectors for my subspace W. Now recall that W2 is the vector that the orthogonal projection of U onto the orthogonal complement of W. So because W2 is in the orthogonal complement of W, it means W2 is orthogonal to every vector in W. And so we have that basically what we have here is that because W is orthogonal to every vector, we have that W2 inner product with VI is going to be 0 for all indices I between 1 and R. Okay, so we can go and because of this, we can go and replace W1 with this whole expression here. And to see this, just remember that all I've done is, in this first term here, I've just added a W2 there. Right, I've done that with the second term as well. I've added a W2 there, and I've done it until the last one. I've added a W2 there. And the reason I can do this is because W2 is going to be orthogonal to each one of these vectors. Right, so basically, if you go and work that term out there by my axiom, that becomes the inner product of W1 with V1 plus the inner product of W2 with V1, and this term, that term there is just going to be 0 because the vector W2 is orthogonal to the vector V1. Right, so I can pretty much do this for all the terms. I can just go and add a W2 to each one of all of them, and it's not going to make a difference. Right, so at the very end, we can then, W1 is the projection, as we said, of U onto W, which we said is this whole term here. And then we did that replacement I talked about. And then we can just replace W1 plus W2 with the vector U. And we prove our result. Okay, so let's look at this example. Here they give us the subspace spanned by those two vectors U1 and U2. U1 is a 2 by 2 matrix. We're working in M22, the vector space of 2 by 2 matrices. And how we define the inner product in this case is we define it as A1 times B1 plus 2 times A2 B2 plus 2 times A3B3 plus A4B4, where A is this matrix and B is this matrix here. Right, now they ask us if V is this vector, find the projection, orthogonal projection of V onto the subspace W, and also find the orthogonal projection of V onto the orthogonal complement of W. So now it's just pretty much applying the previous theorem and just using the given, using the inner product that is given. Okay, so firstly, let's just check that the subspace, this is a basis for the subspace. Let's just make sure that it's an orthogonal basis. So we just take the vectors u1 and u2, we take their inner product. How does the inner product work? Firstly, you take the first entry there and you multiply it with that entry there. Then you add that to twice the second that entry there multiplied by that entry there, plus twice that entry there multiplied by that entry there, plus this entry here multiplied by that entry there. So that all adds up to 0. So u1, u2 is an orthogonal basis for W. So that then, it means that it follows that the projection of V onto W by definition is going to be this linear combination. This follows straight through from the previous theorem, where that V is that vector there, and u1 and u2 come from the orthogonal basis. Now, having said that, what we need to do is we need to find the norm of u1 and we need to find the norm of u2. And to do that, we are basically going to do, we're going to apply the rule that we have been assigned. Okay, so what is the orthogonality rule that we're talking about here? Okay, or the inner product rule. So what it means is taking the inner product of u1 with itself. Firstly, you're going to multiply that term with that term, and then you're going to add that to twice this term multiplied by that term. Let's look at the orthogonality. What the orthogonality looks, or what the inner product of u1 with itself looks like. First of all, the inner product rule works as follows. You take this term and you multiply it with that same term. Then to that you add this term multiplied by that term itself, because you're taking the inner product of u1 with itself. And then what you do is you add that to twice that term multiplied by itself, and then you add that to that term multiplied by that term, which is this term here. Now adding all of that together, that is going to be basically, that's going to give you 5. Alright, so so this term here that we've worked out is in actual fact 5. Now we need to find the norm of u2 squared, and we can do that by taking the inner product of u2 with itself. And again, this is exactly the same procedure. We are going to look at the rule that we've been assigned, and what that is going to be here is we're going to take u2 and then we're going to multiply the first term with the first term, plus twice that term multiplied by that term, plus twice that term multiplied by that term, plus that term multiplied by that term, and that is going to give you an answer of 7. Right, so plugging that in, the projection of W of V onto W, that is going to be, first of all, we have to calculate that and have to calculate that, but we can plug that in so long. We can plug that in so long, right? So we work that out as 7 and 5 respectively. Now, if we take the inner product of V with U1 and the inner product of V with U2, that works out to the given terms. And again, the reason for that is recall what my V was. So if we take the first one, we take the inner product of V with U1. So it's going to be this term multiplied by that term plus twice this term multiplied by that term plus twice this term multiplied by that term plus that term multiplied by that term. Okay, so that will give me an answer of -1. Then if we take the inner product of V with U2, again it is V with U2, that term multiplied by that term plus twice that term multiplied by that term plus twice multiplied by that term plus that term multiplied by that term. And that is going to give me an answer of -1. Right? So going back there, we can replace both those things that I worked out. That we can replace with -1, and that we can replace with -1. And so we've got our vector, new projection vector. And we can just go and just write that down and get and simplify. Right, so basically this projection vector is that 2 by 2 matrix. Now to find the other projection of V onto the orthogonal complement of W, that is going to be, it's going to be by definition, it's going to be V minus the projection of V onto W, the orthogonal projection. That we worked out as this, and V is the identity matrix, and then adding all that together we get this end result. Okay, so that is how this projection theorem, how it works. Okay, so now we can go on to the Graham-Schmidt technique for taking basically what we're going to do is we are going to take a basis for a subspace, and then we're going to take this basis and turn it into an orthogonal basis. Okay, so Theorem 5 deals with the fact that every non-zero finite dimensional inner product space has an orthonormal basis. Okay, now what they're saying here is that you can so what we want to, we're proving it actually with a Graham-Schmidt algorithm, which you're going to do now. So you're going to take a basis, and then you're going to from that basis construct an orthogonal basis, and then an orthogonal basis you can just make it an orthonormal basis by dividing each vector by its norm. Okay, so how does the Graham-Schmidt method, how does it work?